So having set up the problem of wanting to predict the probability distribution on the outcome space, so our action space is now probability distributions, we have a few things to sort out. One is when we make a probability distribution prediction, how do we evaluate how good it is? Another is how are we even going to represent a probability distribution? Okay. We had graphs that were, kind of complicated objects representing it. What's the way to produce a probability distribution? And then how do we actually fit the probability distribution? So maximum likelihood. Likelihood will be our tool for assessing the quality of fit, and our fitting procedure will be to maximize the likelihood, giving maximum likelihood estimation. So first, we produce a probability distribution, an estimated probability distribution that we hope to resemble the true distribution for a given input. How do we measure how good it is? And the idea is that we want it to be a good estimate for data that comes in the future. So for simplicity, in fact, this method is specific for the situation in which the distribution that we're predicting is either a density function or a probability mass function. So discrete probabilities for different inputs, or a continuous probability density function. And so typical outcome spaces we'll be talking about, we have reals or RD, binary classification, -1, 1. Multi-class is now something we can address today. So maybe you have k+1 classes. Unbounded counts, like in our taxi pickup problem. All these are potential outcome spaces, and we're going to be able to want to put distributions on each of these outcome spaces. So how do we evaluate? So someone gives us an estimate p hat for the distribution of y. How do we evaluate how good it is? And one idea is that we want it to be descriptive of future data. And how can we evaluate that? Let's draw a quick picture. So suppose so we're going to draw predictive distributions. If I did that, what would the x-axis be? Because what's the distribution over? Input space? Outcome space. The predictive distributions are on the output space, right? It's going to be classification or something like that. And so suppose I predict, suppose this is a nice continuous outcome space, -10, 0, 10. And we might predict a distribution on this. We would want to predict a density. So maybe we predict a density that looks like this somehow, right? So using training data, or however we did it, we came up with a density that we're predicting for outcome y. And this is the prediction we make. And then we observe some outcome, right? So the outcome corresponds to some point on this y-axis, maybe here, maybe here, maybe here. All right. So the intuition is that if this is our predicted distribution, and this is the point that shows up, our distribution doesn't look so great if this is the point that shows up. This seems relatively unlikely, this point. But if our predicted distribution were this, and this point shows up, that seems a lot more favorable for the distribution we predicted than this one. So if this point shows up, that's lending a lot more support that this predicted distribution was a good one than this point or than this point. Now, this is a density. We'll write it. We'll write p hat of x. P hat, of course, because it's our prediction, it's our estimate. And I wrote x here, but that's not right. We want to call it y because it's soon going to be an element of the outcome space, so it should be a y. And so this is a number. It would be this value, that would be like p hat of y would be that height. Okay. And this number is called a likelihood. So it's a term that's used whether we have a density in this case, or the alternative is a probability mass function. So if our outcome space y is discrete, suppose it's classes. So we have class 0, 1, 2, and 3. And then our prediction, our predicted distribution would look something like, could represent it like this. Separate bars. Okay. And then the y-axis would be probability. Point 0.2, 0.5, 0.2, 0.1. All right. So here, p hat of like y equals 2 would be equal to 0.2. So we could call this the likelihood. In this, for the discrete case, the likelihood is also the probability of the event happening. So the probability that y is 2 is predicted to be 0.2. But in this case, one can't interpret, I don't know, maybe this height is 1.6, could be. So we can't interpret that number as a probability. It's not a probability. It's the density value. It's called the likelihood. Okay. So what we're generally looking for is likelihoods that are large. We want a predicted distribution that assigns high likelihood to the outcome that actually occurs. So we want p hat of y to be large, essentially. All right. So suppose we now have a collection of data, y1 through yn, and we have a predicted distribution, p hat. And so what we want to assess is how high of a likelihood does p hat give for all the data that we observe. Now we assume the data is independent, so kind of this likelihood of all the data should factorize into the products of the likelihood of the individual observations. And this would be called the likelihood for the prediction of the prediction for the data D. Okay. And as we mentioned, if p hat is actually a probability mass function like this, then the likelihood is also an actual probability. If it's a density, we can only say likelihood. All right. So this is our general strategy to assess performance. All right. So that's performance assessment. And now we need to talk about distribution representation. What does it mean to produce a distribution? And we're going to, not just us, people generally keep things simple and use parametric distributions. And a parametric model or a parametric family of distributions all mean the same thing. So a parametric model is a set of probability distributions indexed by a parameter theta. So the parametric piece is simply that every distribution in a set of distributions can be specified with a parameter theta. Theta is typically, in our case anyway, will be real valued or RD, a real valued vector. All right. So this sets up this correspondence between a parameter value and a probability distribution. And so in that case, if we want to predict a probability distribution from this family, we can just produce theta, the parameter corresponding to that distribution. And that'll be the strategy we'll use for representing distributions. All right, so if we're going to do this, we should have a few distribution families at our disposal. So we'll go over a few just as a quick review. But when you're actually working on a problem, you should do a little research on distributions that are kind of known and described in the literature. You might find something that's very appropriate for the data that you have. But just to get us started, Poisson. So when you describe a family of distributions, there's a few things that one needs to talk about. One is the support of the distribution. So the support of the distribution is kind of the set of all values that can possibly occur. For a density, the support would be the set of the space that has non-zero density. All right? For a probability mass function, it's any part of the input that has non-zero probability. So that's the support. And whenever you're looking up a distribution, it's very important to read the support, because two distributions can differ only on the support. They could have the same form of the density, but just be cut off at different points. And the parameter space. So for a Poisson, the parameters are, we have a single parameter, usually called lambda, but we're only allowing lambda to be greater than 0. So it turns out lambda for a Poisson distribution is the mean of the Poisson distribution. Poisson is for counts. Counts have to be 0 or larger, so this would make sense that the mean has to be non-zero. Okay. And the probability mass function has this form. And here's some examples of probability mass functions for the Poisson distribution. Note that we have a dot only at the integers, the non-negative integers, because it's a distribution on counts from 0 to infinity. Different parameter values give you different probability mass functions. So lambda is 10 is this curve. You can see its mean looks plausibly around 10. Okay. So this is the simplest example for distribution on counts. Beta family is interesting. So here, the support is the unit interval 0 to 1. So we're in a continuous regime now. When might you want a distribution on the interval 0 to 1? Yeah?
Probability.
Yeah, so suppose you have a probability. A probability is between 0 and 1. If you, for some reason, wanted to put a distribution on a probability, that's a good support for your distribution. And we will, in fact, do this next week, or whenever we do Bayesian statistics, where every parameter gets a probability distribution. And if our parameter is a probability, we need a distribution on the range 0 to 1. So the beta family is supported on 0, 1, which is nice. And it's a 2-parameter family. Alpha and beta have to both be specified to get a beta distribution. And again, these are both non-negative parameters. So what are some shapes looking like? Again, so this time we'll see that these are continuous. These are densities supported on 0, 1, which is to say they'd be 0 outside of that interval. And you can see a wide variety of shapes of distributions are possible with the beta distribution. It's a nice, flexible family of distributions. All right. Gamma family. The support of the gamma family, 0 to infinity, positive real numbers. So here, start at 0 and goes off, and you can see the different shapes of the gamma family. That's also 2 parameters, very flexible distribution. Certain other well-known distributions are special cases of gamma, exponential, these sorts of things. Okay. All right, so this is just a taste of the very many kind of well-known, well-studied parametric distributions that are out there. But I want to give you, for kind of very distinct supports, here are a few types of distributions to look at first. Again, for counts, negative binomial is another good one. I don't have a good image of that here. But okay. All right. So we're making rapid progress here. We've discussed how to evaluate a predicted distribution. We're going to use likelihood of data. And the set of distributions that we're going to consider producing, we're going to restrict to a parametric family of distributions. We could pick any parametric family of distributions we like, but once it's chosen, we're always predicting something from that class. Okay. So finally, how are we going to choose our estimator for a particular distribution? And as kind of our usual pattern, when you know what you want, you try to get the thing that maximizes that. The analog for empirical risk minimization was we knew what we didn't want, that's the loss, and we try to minimize that. So here we're kind of doing the reverse of maximizing what we do want, which is high likelihood. So just write that down. So again, the likelihood for the parameter estimate now, because we're estimating distributions via their parameter, theta hat, for the sample D, write as the product of the likelihoods for the individual observations, yi. But sometimes it's easier to work with the log of this. And that's called the log likelihood. And the reason is that when you take the log of the product, this breaks up into the sum of the logs, right? Standard log of product is sum of the logs. And it's much easier to handle sums than products for things like differentiation and that sort of thing. OK. So the maximum likelihood estimator theta hat is, for a particular parametrized model, is exactly the theta that maximizes this log likelihood. And so this is an optimization problem. So maximum likelihood estimation is an optimization problem, just like empirical risk minimization was an optimization problem. And in fact, we can use the same techniques that we've used so far, assuming that our kind of probability, our likelihood function, our p, is nice enough. So sometimes we can use calculus and get a closed form, just like we can get a closed form empirical risk minimizer. Sometimes we can use stochastic gradient descent methods or gradient descent methods. So the usual thing for doing optimization. So you're well equipped now to solve these maximum likelihood problems. All right, so one thing that we should mention is that maximum likelihood estimators don't always exist, but usually there's some good reason for it. It's not like an unexpected non-existence. So for example, suppose we have a Gaussian family of distributions, two-parameter Gaussian family, so unknown mean, mu, and unknown variance, sigma squared. Suppose we only have a single observation. So what goes wrong if we're going to try to find the mu and sigma squared that give that observation the maximum possible likelihood?
There could be multiple.
So one issue is an issue of non-uniqueness. Maybe there's multiple ones. Well, in general, there could be maximum likelihood is not unique. That's true. I don't know if that's quite the issue here, though.
Let's give us some board space.
So you won't have sigma equals 0. You won't have sigma equals 0 in that case.
OK. I'm hearing the beginnings of an answer here. So I think you had an idea?
Delta at y.
OK. You have a delta at y. So the issue is that suppose our observation here is y. So it seems obvious that we should have our mu equal to y. But what should sigma squared be?
0.
Yeah, well, OK, good. So sigma squared should be as small as possible. But as you make it smaller and smaller, what happens to the likelihood of y? I mean, can you really have sigma squared equal to 0? You can't. Sigma squared equal to 0, well, it's outside the domain of allowable parameters. Why is sigma squared equals 0 not allowed? This is not a distribution anymore. Well, you could include, if you wanted to, a distribution into this family that puts probability 1 on y. But that's not generally considered a Gaussian distribution. So with this Gaussian family, the MLE doesn't exist because the maximizer will be sigma squared equal to 0, and that's out of the parameter space. OK. All right. So, yeah.
Does likelihood go to infinity? Is it bounded?
No, so this is the example of likelihood going to infinity. As sigma squared goes to 0, the likelihood of y would go to infinity. That's right, yeah. Yeah.
So we said we can use SGD for optimizing the MLE. Is it, can you always tell it's going to be convex or? So
the question is, I claim you can use SGD to optimize this objective function. And the question is, how can we tell if it's convex? So no, there's nothing I've said so far that makes this convex. Absolutely, we want for a lot of the examples we have today, it will be convex or concave. But these days, we're not too scared of non-convex functions with SGD. Neural networks are not convex, for instance. We seem to get good results on that. But any method that's kind of classical probably is convex or concave. All right. So let's go back to the taxicab pickup problem. Let's do a Poisson fit and see what that looks like. So kind of working out the math a bit. So we have counts over, let's say, n weeks. Let's suppose we're doing the highly stratified version, where we're looking specifically at the Penn Station grid cell on Mondays from 7 to 8 p.m. In our data, we had 27 weeks, 14 weeks for training. But here we're generalizing a bit to n weeks. And we want to fit a Poisson distribution to this data. So we start with the kind of performance of a single prediction for a single count. So this is the log likelihood for a single count k. What's our prediction? What would the prediction amount to in this expression? Kind of there's a prediction lurking in this log likelihood. Lambda is a prediction. Great. Lambda is the predicted parameter for the Poisson distribution, right? It's the mean of the Poisson distribution. And then this expression evaluates how likely, or in the Poisson case, what's the probability of the count k that was actually observed under the probability distribution Poisson lambda that we predicted. Great. And you can write it out. Looks like that. This is just plugging in the density, rather the probability mass function from the Poisson distribution. And then we can write the full log likelihood by combining all the data. It comes out to the sum of the logs, of course. And if we wanted to do maximum likelihood estimation, how would we find the maximum likelihood lambda for this data set D? Yeah?
Differentiate with respect to that?
OK. So you can differentiate this expression with respect to, the end goal is to maximize this expression. So one approach would be to differentiate it and use one of our kind of iterative gradient methods, for instance. Yeah. All right. So we have the full log likelihood. As you suggested, we can differentiate and solve for the first order conditions, which will give an expression for lambda. And yeah, it turns out to be exactly the mean of our observed counts. Great. All right. So here it has been applied to our Penn Station counts. So what we've done here is we've done 3 different fits. Let's start with 3 different fits on the training set: Poisson, negative binomial, and the histogram. Right? And then we go to our test set and we compute our test log likelihood. And we get these numbers. So first of all, which is the best test log likelihood? Negative binomial, because it's the largest. It's a little odd. Our log likelihoods are often negative. So, but yeah, negative binomial is the largest. So that, in some senses, is the best by the performance measure that we are talking about today. What's going on with histogram, negative infinity? What might be happening there?
It is not a good, it doesn't fit the data.
Yeah, in some senses, it seems to be a poor fit for the data, yeah?
Bin width is too low.
Say again?
The width of the bin is too low.
The width of the bin is too low. Perhaps that could be something that went wrong.
The currents doesn't exist. In the histogram is 0.
OK. So if the histogram that we're estimating gives probability 0 to a bin that shows up in test, then we're going to be in big trouble. So on training data, we come up with these empirical bins these bins and we have our empirical estimate of probability for each. So maybe this is 0 pickups, 1 pickup, 2 pickup, and 3 is 0. Maybe 4 has 1. Okay. So suppose at test time we see a 3. We see 3 pickups. So our predicted probability distribution gave 0 probability to that. Right? So the log of 0, the log likelihood, will be negative infinity. Log of 0 is negative infinity. So that's how we end up with this negative infinity for the histogram estimator. It assigns 0 probability to something that happened. Very bad. So one thing you can do, histograms are nice on the other hand because they're very flexible. They're not constrained to any particular parametric shape. So here, for instance, we did a combination of 95% histogram and mixed that with 5% negative binomial prediction. So the negative binomial is safe because it assigns some probability to every possible value. The histogram potentially could be a little bit more detailed or adaptive in its fit. In this case, it doesn't do as well as negative binomial, but it's certainly better than negative infinity. Okay. And that's a strategy one can use, yeah.
But for the trained data set, this is the best one to describe.
Yeah, for the trained data, this is the best. That's true.
But the test set these numbers are also kind of random, because you may come up with a different test set.
Yeah, so that's right. So each of these numbers is in some sense an instantiation of something random because they're based on a randomly drawn test set. That's right.
That's right.
So it's overfitting.
What?
It's overfitting. Infinite trinity.
You could call this an overfitting situation, yeah. But it's a very specific kind. It's a particular oddity of the histogram estimator combined with likelihood that gives you this negative infinity, which is, we've never seen like infinite loss before. So this is the first time we have something that's this a little odd. So a little bit more than just to say overfitting here.
Sorry, can you write down the log likelihood for
The log likelihood for?
the Instagram?
Yeah, sure. Sure. All right. So first of all, so the question is, let's get a little bit more specific on this log likelihood for the histogram. So first we need to represent the probability distribution estimate given by the histogram. So I will convert this to a table form. So the histogram estimate we're producing this is count, and this is the probability estimate for that count. So 0, let's say, is 0.2. Count of 1, let's say, is 0.4. Let's say 0.2 again. 0, 2, 4, 8, 0.2. Can you see? All right. So all right, now let's say we have some data. Data D, it's a collection of counts. Let's suppose the counts are 0, 3, 1, 2. All right, that's good. Okay. And now what we want is the likelihood of this data, the likelihood of our estimate p hat. This is our histogram estimator. This is, we can write this as p hat of y. Let's call it count y. Did we say y or k? I think it counts k. P hat of k for count k. So this table represents p hat. Right. And now the likelihood of p hat for our data is p hat data, which is equal to the product. We assume these are independent samples, so it's like the product of these probabilities. Right? Okay. So what's p hat of 0? 0.2. P hat of 3 is 0. P hat of 1 is 0.4. p hat of 2 is 0.2. Okay, so the likelihood for the data D is 0. The log of the likelihood is negative infinity, because log of 0 is negative infinity. Okay. As long as we're here, negative binomial would also give probabilities. So negative binomial would give some other probabilities here. And now you can see what 0.95% times histogram plus 0.05% of negative binomial would be. That would just be blending these two probabilities into a new distribution. Questions? Follow up?
So if you use the train set, fitting the train set, what number it will get?
Okay, so if we put training log likelihood up here,
Yeah.
what numbers would we get in the sense of which would be the best?
We'll also get 4 numbers here, right?
Okay, we'll get 4 numbers, that's right. So what's the question, sorry?
Will that show the same thing?
Well,
It will not show the same thing.
You certainly won't get negative infinity.
Not get, yes, but for the other things,
What characteristic of this result are you wondering whether it will occur in the training result?
I'm wondering if you have training set, you will have the best one is in the histogram.
Yeah, so the question is histogram always the best? And you think it will be, but it depends on how you do the bins of the histogram. So it depends how much you stratify your space Y, right? So here, with this binning, we were very stratified. You could not have had a finer decomposition of counts K, because every single count got its own probability. If we had the same breakdown for the histogram on the training, that would be the best. That would beat the others, absolutely. But if we combined bins, then it may not do as well. Yeah?
Okay, so bin width 1 will always be your training MLE, but not
Bit for discrete data, if you treat every possible observation as its own bin, then yes, the maximum likelihood histogram with that bin width will beat all other parametric distributions. That's right. Yeah. On training, and then yes, if that may perform poorly on test, and that would be an instance of overfitting. An extreme example is negative infinity on test log likelihood. All right. All right. Great.
What is the last one?
The last. So the last, this is a blending of two distributions. So given two probability mass functions, you could take 0.95 times one of them and 0.05 times the other and end up with a new probability mass function. And that's what I started to write here. So a negative binomial number, I don't know what reasonable probability mass functions would be for negative binomial, but I know they're always non-zero. And so maybe it's like 0.18, 0.39, 0.26, 0.11, 0.08, et cetera. It would keep going to infinity. We'd always be non-zero. And then we could take a linear combination of these two distributions and create a new one.
That doesn't sum to 1.
This column will sum to 1. This column sums to 1. And 90.95 times this plus 0.05 times this will also sum to 1. And so that will be a new distribution. And the advantage is if you really like this histogram estimate, but you are worried that it might sometimes be 0 and that would be a disaster, you could blend it with something you know will always be non-zero a little bit. Yeah. Okay.
So the test log likelihood will always be negative, right?
No. So test log likelihood, will it always be negative? I don't think so. What? Oh, because 1 is, Yeah, so you have in mind that 1 is the maximum value and then log of 1 is 0. So this is true for probability mass functions. Probability mass functions are actual probabilities, which are, yes, correct, less or equal to 1, and so log probabilities will always be negative. That's true, but you also have likelihoods for continuous distributions, and density values can certainly go above 1. And so the log of those density values may be non-negative, may be positive. But yeah, this is a good point, that for probability, for discrete distributions that are giving probabilities, yes, the log likelihood would be negative or 0. Okay, so as was commented earlier, just as in classification and regression, maximum likelihood can overfit. And so just like we had nested hypothesis spaces in a certain sense in our empirical risk minimization framework, you could think of probability models as getting more and less complicated. So for instance, negative binomial distribution is in some sense a richer collection of distributions than Poisson. Histograms with 10 bins is in some sense simpler distribution than the histogram with a bin for every possible value of y, which for instance would be complete overfit for continuous data. So how are you going to judge which model works best? You have this model selection issue, and then the answer is we're going to look at likelihood on holdout data on validation set. Okay. All right. So let's take another short break, and then we'll wrap up with actual conditional probability models in a bit.